Hello and welcome to GCSE Physics tutorial for topic P1 Energy. This tutorial will cover work, power and efficiency, and energy and heating. We'll also be looking at two practicals, looking at thermal insulators and specific heat capacity. First of all, work and power. Power is the rate of energy transfer or rate of doing work. 1 watt is also the equivalent of 1 joule of energy transferred per second. There's two calculations for power that you need to know. Power is energy transferred over time, or power is work done over time. Work done is force times distance, as shown here. Efficiency. This can be calculated by the useful output energy transfer divided by the total input times by 100 to get a percentage. Look at this example here. 180,000 joules of the energy was useful. You divide that over how much energy went in, which is 200,000, and that gives you 90% efficiency because 20,000 joules was wasted. The less energy something wastes, the more efficient it is. Nothing is 100% efficient because all devices will waste some energy, most often as heat, sometimes as sound. You can reduce unwanted energy transfers and make things more efficient. For example, lubrication, that means there'll be less friction, so less energy is wasted as heat. Another example is insulation of the home. This prevents heat loss and makes it more efficient to heat your house and not lose any heat. There's some examples of this. Loft insulation, that reduces convection. Cavity wall insulation, which is when foam is put into the walls of the house, that also reduces convection. Double glazing, that reduces conduction, and draft excluders, which are put underneath the doors, that reduces convection. You obviously need to know what convection and conduction mean, so let's go into those. Conduction. This occurs in solids. If you look at the diagram here, if you heat a material that is a conductor, the particles start to vibrate. As they start to vibrate, they move faster and pass on the energy through the material, so eventually all of it becomes hot. This is passing on thermal energy from particles to other particles, and when they move, the particles have kinetic energy. This occurs in solids because the particles are close to each other. You can measure the thermal conductivity of different materials. This is a measure of how quickly energy is transferred through it. If you get 3 different metals like this and place on the end a drawing pin stuck on with Vaseline, if you then heat one end and then time how long it takes for the Vaseline to melt and the pin to drop, you can then find out which is the better conductor because it'd be the one that the heat moved along faster and melted the Vaseline. Convection. This occurs in liquids and gases because it involves the particles moving. When particles are heated, they move faster. We know that already. They then start to become less dense and spread out, and that makes the particles rise, so heat rises. When it rises, the particles then start to cool down, and then they get more dense, and that causes them to sink. Then they get heated up again, and the cycle continues. That is called a convection current. So this is an example of how a radiator ends up heating up the whole room, or how hot air balloons can be controlled. There's also convection currents underneath the Earth's crust, which causes the crust to just move a few centimetres a year. And this is also an example of how the heating element at the bottom of a kettle will heat up all of the water in the kettle. One of the practicals you need to know is how to test different thermal insulators. What you can do is get a beaker and boil some water and put it into the beaker, and then cover the beaker with different materials, for example newspaper. Make sure there's a lid on as well because otherwise a lot of heat will escape from the top. You measure the initial temperature and then leave, and then record the final temperature. And then you can repeat this with different layers of newspaper or other insulators like bubble wrap or cotton wool and see which is the best at keeping the heat in. So which one did the temperature drop the least with? Another practical is to find the specific heat capacity. This is the amount of energy needed to raise the temperature of 1 kilogram of a substance by 1 degree. Celsius. The change in thermal energy is mass times specific heat capacity times temperature change. So you can rearrange this to find the specific heat capacity of a material. To do this practical, you would need an immersion heater or something that can heat up the material. So imagine it's a block of aluminium or something like that. That's what you're trying to find the specific heat capacity of. You'll also need to have holes in the material so you can put thermometers into it. You need to insulate the material as well to make sure no heat is lost from it. You record the initial temperature of the material and then you would connect the heater that's inside to the power and turn it on for about 10 minutes. So this will heat up the material. And then you record the highest temperature the material reaches and see how much the temperature has risen. And then from that you can figure out the specific heat capacity using the equation above. Here's 3 questions. If you pause the tutorial and try these now. Thermal conductivity is a measure of how quickly energy is transferred through a material during conduction. How does a radiator heat up a room? Well, the particles near the radiator get hot, they spread out and become less dense, so they rise. They then cool down and become more dense and sink. Then closer to the radiator they heat up again and then rise, and this continues in a cycle to set up a convection current and the whole room warms up. What's the efficiency of a light bulb that uses 800 joules of a total input of 1000 joules? So it'll be 800 is useful divided by 1000 that went in, which is 80%. Also in this example, 200 joules has been wasted. What's the power of a motor that transfers 5 kilojoules of energy in 2 minutes? So remember, you need to convert the energy, 5 kilojoules, into joules. So that'd be 5,000 joules. And minutes, you need to put that into seconds. So it'd be 120 seconds. So you do energy transferred divided by time. So 5,000 divided by 120, which gives you 41.7 watts. In summary, we've looked at work, power, efficiency, energy and heating, so conduction and convection, and 2 practicals.